Muy buenas tardes, bienvenidos de regreso. Esperamos que
Good afternoon and welcome back. We hope you enjoyed launch. So now we're going to continue with the agenda for this afternoon. We're going to begin with the next panel about recent research studies about DDGs. Regular or conventional DDGs and new generation DDGs. This virtual panel is going to be moderated by Dr. Pedro Urriola, and we're going to have presentations by 4 students. These presentations were pre recorded, but they're going to be with us live, and they're going to answer questions live at the end of their presentations or at the end of the whole block. We're going to have a question and answer session. So I would like to introduce Dr. Pedro Urriola. He's a veterinarian from the Central University of Venezuela. He completed a master's degree at Minnesota University and he has a PhD in equine nutrition at Illinois University. He also worked at Cargill Animal Nutrition in Del River, Minnesota, as manager of development and investigation for swine. Currently, he works for the University of Minnesota, where he uses modern techniques to evaluate or analyze nutrition with sub-industrial products in cooperation with integrated animal biology. He also works with investigation of swine disease in collaboration with the School of Veterinary Medicine. He's also the co-author of more than 50 publications and different chapters. He's written different chapters for other important publications. So welcome, Dr. Orriola, and please go ahead and continue as the moderator of the panel. Thank you very much. Good afternoon. I'm quite happy to be here, quite grateful for this idea of the U.S. Grant Council that brought this innovative model of bringing students to present their projects. I remember that I studied with a professor by the name of Jerry Churson and Hans Stein, and they were people that began working with DDGs many years ago. And I remember that Dr. Stein and Dr. Schuson used to travel around the world speaking about or sharing their knowledge, sharing what we had developed and learned in our laboratories. But again, I love this idea that now we have students that are actually doing the investigation, doing their presentations, presenting their work. This is sort of like introduction to research course for future researchers, and being connected to the industry is quite important for students. So we have a student for poultry. Another student is going to speak about swine. Another student is going to speak about aquaculture, and the other student is going to speak about dairy cow. Um, to make sure that we have time for questions and answers, again, these students are connected. They are connected live right now. You can talk in English, you can speak in English, and they will hear the simultaneous translation, including questions and anything else that you might say. So please use your translation radios, your translation devices, so we can all communicate in our own languages without any difficulties. So without any further preamble, again, the first presentation is by Ben Parsons, and its title is Standardized Amino Acid Stability. Ben, the floor is yours. Please go ahead, Ben.
Today and share some of the work that we've completed looking at the standardized amino acid digestibility, true metabolizable energy, and some of the more recent relative bioavailability work conducted. As a brief introduction, DDGS production increased substantially in the U.S. over the past 2 decades. However, due to more recent variability in ethanol price, as well as long-term concerns with decreasing ethanol demand as we shift towards utilizing electric vehicles, There is an increased emphasis being placed on trying to develop alternative revenue streams that ethanol plants can use, and this has led to the development of systems that are capable of producing high quality increased protein corn co-products that are more consistent in their nutrient composition compared with conventional DDGS. There are two main types of fractionation systems that exist. The first type is front-end fractionation systems, where the corn kernel is fractured before fermentation has occurred. Three previously researched front-end systems include the quick germ, quick fiber, and enzymatic milling systems that can increase the crude protein content from 35 to as high as 59% crude protein. And typically, studies have also reported an improved amino acid digestibility for these products as well. The second type of fractionation system, which will be the emphasis for the samples that we looked at in this study, were back-end fractionation systems. And two previously researched systems for these back-end processes are the elusive process that utilizes a combination of sieving and air elutriation to increase the crude protein content to 41%, and a process that is owned by Fluid Quip Technologies where it utilizes a combination of fiber washing as well as protein filtration, washing, and drying to produce a product that contains approximately 53% crude protein on a dry matter basis, and was also previously reported to contain high amino acid digestibilities ranging from 84 to 94%. And the main difference between the back-end fractionation and the front-end systems is that the back-end is fractionating the DDGS after fermentation has occurred. The first three experiments were conducted to look at the standardized amino acid digestibility values and TMEN of corn fermented protein, high protein DDGS, and a reduced fiber high protein DDGS, all utilizing the precision fed rooster assay. There were three sets of samples that we looked at in these experiments. The first set came from ethanol plants utilizing the system developed by Fluid Quip Technologies, where we evaluated 2 samples of a conventional DDGS and 8 samples of their corn fermented protein product. The 8 CFP samples were obtained from several ethanol plants over a 3-year period of time. And as of last year, they were producing approximately 500,000 tons of CFP annually, but this was expected to increase rapidly over this year. The second set of samples came from the Bransenburg system, which utilizes a sieving method. And we looked at 2 samples of a high protein DDGS from this system. And the last system we looked at was owned by ST Equipment and Technologies, which utilizes a electrostatic separation method. And from this system, we looked at 2 samples of a conventional DDGS, 2 samples of a reduced fiber high protein DDGS, and then 1 sample of the low protein DDGS, which is the residual fraction left after that reduced fiber high protein fraction has been recovered. Here I have depicted the process used to produce the corn fermented protein. There's a variety of steps involved to produce this fractionated product, but the main ones that I want to highlight here are that pressure-fed screens are utilized to remove the fiber fraction. They then use clarifiers to recover the crude corn oil, and then protein decanters are utilized to produce the CFP product, which on an as-fed basis is expected to contain at least 50% crude protein. And one main advantage of this system is it still allows for production of a conventional DDGS and the crude corn oil, which we would have in our normal conventional DDGS processing. The STET system is quite different from the Fluid Quip system in that it uses an electrostatic separation method. So how this works is the DDGS will flow onto a belt, and then they're able to induce charges to the particles and separate the fiber and protein based on differences in the charges of those particles, and that allows them to obtain that reduced fiber high protein fraction. In each of these experiments, we utilized the precision-fed rooster assay, where conventional roosters were used to determine the TMEN, and cystectomized birds were used to determine the standardized amino acid digestibility. There were 3 to 6 individually caged roosters per treatment, and each experiment consisted of fasting the roosters for 26 hours, after which they were crop intubated with 24 or 30 grams of sample. And then we quantitatively collected excreta for the following 48 hours, freeze-dried it, and then analyzed it for gross energy, nitrogen, and amino acids. For statistical analysis, the data from all these experiments was analyzed in SAS for an ANOVA procedure for a completely randomized design, which was followed by Fisher's least significant difference test. The individual rooster was used as the experimental unit for the analyses, and the means were considered to be different if P is less than 0.05. Now on to the results for experiment 1, where we looked at the corn fermented protein product. The 8 samples of CFP were fairly consistent in their nutrient composition, excluding the third sample of CFP, which contained a slightly lower crude protein and higher TDF content compared with the remaining 7 samples. Overall, the CFP product was found to contain a mean of 56% crude protein on a dry matter basis, which was substantially higher than conventional DDGS, which contained 32% crude protein. The crude fat content in corn fermented protein was found to be slightly lower than conventional DDGS. However, conventional DDGS contained a substantially higher total dietary fiber content of 43% compared with 30% in the CFP product. There were few significant differences observed among the TMEN values for corn fermented protein. However, we did observe that the third sample of CFP contained a significantly lower TMEN compared with CFP 4 and 5. However, all of these CFP samples contained a TMEN that was significantly higher than the conventional DDGS. And overall, we observed that the CFP contained a mean TMEN of 3,556 kcal per kilogram on a dry matter basis, compared with 2,767 kcal per kilogram for the conventional DDGS. We observed few significant differences among the samples when looking at standardized amino acid digestibility values, and overall, both the corn fermented protein and conventional DDGS contained a high standardized amino acid digestibility for all amino acids. Especially of interest, we found that the lysine digestibility values for both products was high, being a mean of 85 and 83% for corn fermented protein and DDGS, indicating little evidence of heat damage during the drying process for those samples. We then calculated the average digestible amino acid contents by multiplying the total amino acids in the feed by the digestibility values. And we found that corn fermented protein contained a higher digestible amino acid content for all amino acids that we evaluated compared with the conventional DDGS. And this was particularly true for the digestible lysine content, which was increased from 0.79% in conventional DDGS to 1.74% in the corn fermented protein product. In summary, we found that the crude protein content was increased from 32% in conventional DDGS to 56% in CFP. The TMEN was also found to be higher than the conventional DDGS, where CFP contained a mean TMEN of 3,556 kcal per kilogram on a dry matter basis. And although the digestibility values for all amino acids were high for both samples, ranging from 88 to 94%, the digestible amino acid concentrations were substantially increased in corn fermented protein compared with conventional DDGs. Now on to the results for the high protein DDGS from the Franzenberg system. We found that the 2 samples of high protein DDGS were similar in their nutrient composition, where they contained a mean crude protein content of 51%, a mean crude fat of 8.5%, and a mean TMEN or TDF content of 35.5%. They also contained a statistically similar TMEN, where the 2 products contained a mean TMEN of 3,325 kcal per kilogram on a dry matter basis. There were few significant differences observed between the standardized amino acid digestibility values for the 2 samples, although we did observe a significantly lower cysteine digestibility value for the second sample of the high protein DDGS. And we also observed a high standardized lysine digestibility value for both samples, once again indicating little evidence of heat damage during the drying process for these ingredients. And the digestible amino acid concentrations were then calculated as I discussed previously, and we observed that the 2 samples of high protein DDGS contained a substantially higher digestible amino acid content for all amino acids evaluated compared with the conventional DDGS 1 and 2 from the last set of samples I discussed. And this was again particularly true for the digestible lysine content, where high protein DDGS contained a mean digestible lysine of 1.53% on a dry matter basis. In summary, we found that the nutritional composition of high-protein DDGS 1 and 2 were similar, where they contained a mean crude protein content of 51% compared with 32% in conventional DDGS 1 and 2. They also, high-protein DDGS contained a mean TMEN of 3,325 kcal per kilogram on a dry matter basis and a high mean amino acid digestibility of 90%. And the digestible amino acid concentrations in the high protein DDGS increased for all amino acids compared with the conventional DDGS. Now on to the last set of samples from this experiment, where we looked at the reduced fiber high protein DDGS from the STET system. We found that the nutrient composition in the two samples of reduced fiber high protein DDGS did vary slightly, where they contained 51 and 46% crude protein and 26 and 21% TDF. The samples did not have a significantly different TMEN, but did vary slightly in their TMEN content. However, the two reduced fiber high protein samples did contain a TMEN that was significantly higher than the low protein and conventional DDGS samples. Overall, there were few significant differences observed among the samples when looking at the standardized amino acid stability values. However, we did observe that the reduced fiber high protein DDGS contained a significantly lower lysine and methionine digestibility compared with some of the other samples. The low lysine digestibility value in particular was pretty clearly evident that that sample was damaged during the drying process, which allowed for formation of Maillard reaction products. And the digestible amino acid concentrations were then calculated using, again, the total amino acids and the digestibility values. And we found that the digestible amino acid concentrations were increased for all amino acids in the reduced fiber high protein DDGS compared with the conventional DDGS. And we generally observed approximately a 0.3 to 0.5 percentage unit increase for most amino acids, or digestible amino acids, and the reduced fiber high protein DDGS compared with the conventional product. In summary, the reduced fiber high protein DDGS contained 48% crude protein and 24% TDF, whereas the conventional DDGS 3 and 4 contained a mean crude protein content of 33% and a mean TDF content of 38%. The TMEN was found to be higher in the reduced fiber high protein DDGS compared with the conventional product, and the digestible amino acid concentrations in the reduced fiber high protein DDGS were also found to be increased compared with the conventional product. The last experiment that I'll cover in this presentation was looking at the relative phosphorus bioavailability value in soybean meal conventional DDGS and NextPro. The NextPro product we evaluated in this experiment is a high protein DDGS that is produced by the company Poet. This this product is very similar to the corn fermented protein product I discussed previously because it is produced using the same back-end fractionation system that's used to produce corn fermented protein. However, the main difference is that NextPro is produced specifically by Poet, and Poet has a unique fermentation method where they use a cool fermentation and they do not use the heating process or a jet cooker during that ethanol production. And we also confirmed that this sample came from an ethanol plant that was using phytates during the fermentation step. And similar to the FQPT or the corn fermented protein system, the production of NextPro still allows for production of conventional DDGS and corn oil. In this experiment, Cobb 500 male broiler chickens were used, and these birds were placed on a common starter diet from day 0 to day 6, after which they were fasted overnight and placed on their respective experimental diets. There were 9 treatments with 5 reps and 5 chicks per rep, and they were fed these experimental diets from day 7 to day 19. On day 19, we ended the trial, and the weight gain and feed intake of the birds was reported, and then the right tibia was collected, autoclaved, cleaned, and then oven dried for 24 hours and ashed for 24 hours in the muffled furnace. The dietary treatments consisted of the first diet being a cornstarch, dextrose, soybean meal, corn, or phosphorus deficient basal diet that had a calculated available phosphorus content of 0.18% and a calculated calcium content of 0.8%. And from this phosphorus deficient basal diet, we created the remaining dietary treatments where we added 2 increasing levels of either potassium phosphate, soybean meal, DDGS, or Nexpro. And each of these test ingredients was added in equal place of cornstarch and dextrose. For statistical analysis, we analyzed the data using the PROC-GLM procedure and SAS for an ANOVA procedure for a completely randomized design, which was followed by 2Ps HSD. The experimental unit for these analysis was 1 pen of 5 chicks, and then after conducting the mean separation, we conducted a multiple linear regression analysis by regressing the bone ash content in milligrams per tibia against the supplemental phosphorus intake of each of the test ingredients, and the effects and means for these analyses were considered to be different at p is less than 0.05. Now on to the results for experiment 4. We found that the nutrient composition of the conventional DDGS and Nexpro was fairly consistent with what we had reported in our previous experiments. The soybean meal contained 53% crude protein on a dry matter basis compared with 31% and 56% in conventional DDGS and Nexpro. The conventional DDGS and Nexpro both contained a fairly low calcium content, and conventional DDGS contained the highest total phosphorus content being 0.98% compared with 0.69% in soybean meal and 0.65% in the Nexpro product. Here I have displayed the tibia ash contents for each of the dietary treatments, and we observed that there was a linear increase in tibia ash content as we added supplemental potassium phosphate to the phosphorus deficient basal diet. We also observed an increase in the tibia ash content as we added the 2 increasing levels of the 3 remaining test ingredients, and the addition of 14% conventional DDGS, which was the highest inclusion level for that ingredient, resulted in a similar mean tibia ash content compared with the highest level of potassium phosphate. Here I have displayed the graph where we conducted the multiple linear regression analysis looking at the tibia ash content regressed against the supplemental phosphorus intake of the respective test ingredients. And when comparing the increase in tibia ash content per unit of supplemental phosphorus intake, we observed the largest increase in tibia ash content for birds consuming potassium phosphate, a similar increase when birds consumed DDGS and Nexpro, and the lowest or smallest increase in tibia ash content per unit of intake of supplemental phosphorus from soybean meal. Using the regressions that I showed on the previous slide, we then calculated the relative phosphorus bioavailability value by taking the slope for the different test ingredients and dividing that by the slope for potassium phosphate. And we then obtained the relative bioavailability values of 33% for soybean meal, 81% for conventional DDGS, and 78% for Nexpro. And after conducting the slope comparison or the mean separation analysis of the slopes, we found that the conventional DDGS and Nexpro contained a similar relative bioavailability value that was significantly higher than that of the soybean meal. And then we calculated the bioavailable phosphorus content by multiplying the total phosphorus by the relative phosphorus bioavailability, and observed that Nexpro contained a bioavailable phosphorus content of 0.5% compared with 0.23% in soybean meal and 0.79% in conventional DDGS. In summary, we found that the phosphorus bioavailability in conventional DDGS and Nexpro was high and was similar, both of which were higher than what we observed for the soybean meal. However, I do want to emphasize that when deciding what coefficients to use for phosphorus availability in high protein DDGS, it's important to consider how that ingredient is being manufactured, specifically whether or not phytase is being added during the fermentation step. And overall, we found that the high protein corn co-products contained a higher TMEN and digestible amino acid content, particularly the digestible lysine compared with conventional DDGS. Nexpro had a high phosphorus bioavailability that was similar to conventional DDGS, and therefore we concluded that the high protein corn co-products contained an increased nutritional value compared with conventional DDGS. And I'd be happy to answer any questions that you have.
Muy bien. ¿Algunas preguntas para Ben? Tenemos a Ben en línea. Si
Do we have any
vaya. Y recuerden hacer las
any questions for Ben? Alvaro is asking again. You can ask your questions in Spanish, and Ben is going to listen to a simultaneous translation of the question. Again, do we have any questions for Ben? And if we have any questions, please wait for a microphone to be handed out to you, and so we can translate the question. Well, Ben, this is Pedro Urriola. I do have a question for you. My question, and again, I work with swine nutrition. I went to school in Illinois with Dr. Hanstein, who has studied digestibility, phosphorus and calcium digestibility instead of bioavailability, based on. And my question is, if with regards to poultry nutrition, is there an effort going on, or is there, say, a benefit if you change the formula based on the digestibility of calcium and phosphorus?
That's a really great question. There is a lot of effort going on to develop both a digestible calcium and digestible phosphorus system. We have several more experiments that we've conducted on that sample we ran the relative bioavailability on, but the analysis is not completed yet. Part of the challenge with digestible phosphorus, and it's not as much seen with swine as it is with poultry, is that the digestibility of phosphorus is highly sensitive to the calcium content you use in the experimental diet, and that can give you values that are not actually additive in your practical diet formulation. So I'm working on that to try to improve that. And the digestible calcium, we have a very long way to go. We have a lot of variability occurring with those values. So we're not very close yet to obtaining a digestible calcium system, but we're working on it.
Muchas gracias, Ben. Tenemos una pregunta por acá.
Thank you, Ben. We have another question.
Sí, buenas tardes. Una pregunta.
My question,
Con estos nuevos productos,
with these new products, is it feasible to,
observar dietas
say, observe or have diets without phosphorus, without inorganic phosphorus, because it is more bioavailable? I do know that this is not the topic of your research, but it's the question that I have. Is it possible? And again, the idea is to determine if it is worth to pay for that product if we eliminate that inorganic phosphorus. And again, that was my question.
Yes, that's another really great question. I know as we move into the later phases, we have in the U.S. observed that we can pull out the inorganic phosphorus sources. And Dr. Rhoda Huskort in Germany has shown pretty clearly that when you add inorganic phosphorus, you reduce the ability of the bird to actually break down phytate. And we're starting to observe that as well and study that. So I think there is a definite, the lights turned off here. There's a definite advantage of doing that. If you can achieve a diet without inorganic sources, you will improve the availability of your plant-based ingredients by increasing the ability of the bird to break down phytate.
Muy bien. Tenemos otra pregunta por acá.
Sí, la pregunta va de nuevo al
Again, question is with regards to formulating with bioavailable phosphorus. If I understood correctly, using phosphate, potassium phosphate. So my question is, when you speak about bioavailability, well, basically there is no literature that indicates if this monosodic phosphate or bicalcium phosphate or potassium phosphate. So the question is, how can you extrapolate that if you do not have a reference point? And you do know that in Europe they have been formulating using digestible phosphorus for more than 20 years. So that was my question or comment again.
Yeah, so with the phosphorus digestibility, that is a major limitation of the study, is that you're having to assume your standard source is 100% available. We pretty well know that no phosphorus source is 100% available. In our digestibility study that we conducted, that we're still working on the results, we did measure phosphorus digestibility for potassium phosphate, which is our standard source. So we will be able to do a sort of conversion for those values after we get the results back to see how when you correct for that difference in actual digestibility of your standard ingredient, how do the values between bioassays compare? But we don't have that data completed yet. As far as formulating based on digestible phosphorus in the US, a lot of the hesitation has been towards variability in values in the literature. They are doing that in Europe, but it gets very difficult to determine whether or not where we're at right now is saving in terms of cost of formulating the diets, though some of the larger companies in the US have stuck with what they know works. And then as we've developed, there is some interest within those companies to shift towards digestible systems. And then there's also some nutritionists that have been around for quite some time that know how to formulate the diets using NPP content the way they've done it their whole career and are somewhat hesitant to switch to a digestible system.
Bueno, muchas gracias, Ben, por tu presentación.
Thank you, Ben, for your presentation. Please, let's give Ben a round of applause.